In this lesson, we are going to continue looking at how to turn our data into information. In the previous lesson, we looked at summarizing categorical data. In this lesson, we're going to look at summarizing quantitative data. Remember that this is data that gives us values are numbers. So the first thing is that we have something called the average. Now, the word we're going to use for average in this class is mean. So the mean is the average. It's denoted by x with a little bar on top, which is usually read x bar. And most of you should know how to find an average already. You add up all of the values that you have and you divide by how many. That is what this formula is saying. I just wanted to introduce you to this notation. So this symbol is the Greek letter sigma. It's the capital letter sigma, and it means sum. So what this thing means is you add up all observations, so all your numbers, and the little sub I thing means you add up your first one, your second one, your third one, etc. And the n is how many. So that says divide by how many. Another measure of central tendency of interest is something called the median. Now, the median is the middle value in an ordered data set. If there are two middle values, then the median is the mean or the average of these two. And just to note, the mean and median are called measures of central tendency. So looking at the center of a data set. So suppose the scores on my quiz for a class of 7 students are as follows. Given these scores, find the mean and median. So to find the mean, we add them all up and divide by how many. So x bar will equal to 91 plus 79 plus 60 plus 94 plus 89 plus 93 plus 86, all divided by 7. So x bar is approximately 84.6. Now to find the median, we have to arrange this into an ordered list. So the lowest number we see is 60. The next lowest appears to be 79, then 86, 89, 91, 93, 94. And the median is the middle value, which we see from the list is 89. Now, one question is, which measure of central tendency is impacted more by outliers? Now, outliers are values that are sort of very different than the values that you're considering. So suppose in that previous example that I had a test score of 10 thrown in there. What would that affect more, the mean or the median? So think about that for a sec. And I think it is the mean. So the mean is more affected. And the reason is that if you look at your median and you throw in one sort of number that's drastically different than all the others, it just shifts where your median is by, a space or a half a space, something like that. But for the mean, you actually add that number in, then you divide by one more than you had originally, and adding that number in changes the sum more drastically. So you can convince yourself that the mean is definitely more affected by outliers. And here's an example to illustrate that. Suppose your grandparents died at the following ages: 25, 70, 80, and 90. And you're just trying to figure out, oh my gosh, how long am I going to live? What do you think is a better indicator of how long you may live, the mean or the median? And let's actually just compare them. So the mean for this data set is 66.25, and the median is 75. Now, which of those do you think kind of illustrates the pattern here? Well, you have lots of relatives that lived, 3 of your grandparents lived to be over 70. So it seems likely that you could also live to be over 70. So 66.25 seems a bit low. So it seems like the median is a better indicator. Perhaps that 25-year-old grandparent was killed in a car accident or a war or some sort of tragic life event and didn't have a chance to sort of live out their potential life for some reason. So it looks like you can see how the outlier of 25 kind of drastically lowered the mean relative to the median. When you have quantitative data, you might also want to talk about how spread out that data is. So the range is the highest value, or the maximum, minus the lowest value, or the minimum. Now the interquartile range is the range between the quartiles, as in you find that using the upper quartile, Q3, and take away the lower quartile, Q1. This is often abbreviated IQR. And then there's something that describes spread called a standard deviation. This is for bell-shaped data only. And we will look at that in the formula for a standard deviation later on in this lesson. But for now, let's look at the range and interquartile range. So 63 college men were asked what they thought was their ideal weight. A 5-number summary of the responses in pounds gave the following information. So first, find the value of the range for these data. Remember that's the max minus the min, and those are also known as the extremes of the data. So the max minus the min is 225 minus 123, or 102. Now the interquartile range is quartile 3 minus quartile 1. And from this part of the table, we see that quartile 3 is 190 and quartile 1 is 155. So the spread between quartile 1 and quartile 3 is just 35 pounds. And recall that this is the middle 50% of people fall within that interval from 155 to 190. And I guess that just answers question C about what percent of the men gave a response that falls in the interval from 155 to 190. That is the middle 50%, so 50%. Now here's how to draw a box plot if you have outliers. So your first step is to decide on what your axis should be based on your data and to label it accordingly. Next, draw a box with the lower end at quartile 1, so Q1, and the upper end at quartile 3. And then we draw a line through the box at the median. We did all this in that previous lesson. Now calculate the interquartile range, IQR, which is found by doing quartile 3 minus quartile 1. And this is how you're going to determine if a number is different enough that we're going to call it an outlier. You draw a line that extends from the lower quartile end of the box to the data value that's not smaller than Q1 minus 1.5 times that interquartile range. So the quartile 1 minus 1.5 times IQR, that's the lowest value that you can be. And if you're lower than that, you're considered an outlier. So that's an outlier on the low end. On the high end, you draw a line from the upper quartile end to the largest data value that's not bigger than quartile 3 plus 1.5 IQR. And then any data points not covered by those lines are dots. The dots are the outliers. All right, so we have the weights for 9 men on the Cambridge crew team are as follows. Find a 5-number summary for these data. So I think it probably would be best to order these data. So the lowest number is 109. The next lowest after that appears to be 178. And then 183. 185, 186, 188, 194, 203, and 214. Let's just count and see if we still have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. So remember that the 5-number summary includes the min, quartile 1, the median, quartile 3, and the max. Now, the min and max are the easiest. So the min is 109, the max is 214. Next, find the median. So since there are 9 values, the middle number is 186. So the median is 186. Now we don't use that median in finding quartile 1 and quartile 3. But to find quartile 1, you look at the lower part of the data and find the median of that. So there are 2 middles there, 178 and 183. So quartile 1 is an average of those. 178 plus 183 over 2, which gives us 180.5. And then to find quartile 3, we look at the median of the upper part of the data. And once again, there are 2 middles, so it'll be the average of them. 194 plus 203 over 2. That gives us 198.5. So those 5 numbers, they constitute our 5-number summary. Now, in this example, we had 1 median, as we didn't average anything to get the median, and then we didn't use that number in finding the quartiles. At least in this text, because there are lots of ways to do this, if you end up with 2 medians, say we have the data set 1, 2, 3, 4, 5, 6, 7, 8. The median here is an average of 4 and 5, 4.5. When you find quartile 1, you actually use that 4. So in that sense, quartile 1 is 2.5, the average of 2 and 3. And same for quartile 3, you use 5 in there. Quartile 3 is 6.5. So that is how this textbook chooses to deal with things. If your median came from 2 values, you then use the lower value when finding the first quartile and the upper value when finding the upper quartile. Whereas when you only have 1 value that gave your median, then you just disregard it when finding your quartiles. Okay, so returning to our original example, let's find the value of the interquartile range. So IQR is quartile 3 minus quartile 1, which is 198.5 minus 180.5, or 18. And we're going to use that number to figure out if certain points, like that 109 or 214, to determine if they are outliers or not. So identify any outliers in the data set. Use the criterion that a value is an outlier if it's either more than 1.5 times IQR above Q3 or more than 1.5 IQR below Q1. So first let's find 1.5 times IQR. So 1.5 times 18 is 27. And here's how you figure out if something is an outlier. You're too low if you're below Q1 minus 1.5 IQR, which is 180.5 minus 27 in this problem, or 153.5. So if you're below 153.5, you're an outlier on the low end. You're too high if you're above quartile 3 plus 1.5 IQR, which is 198.5 plus 27 in this particular problem, or 225.5. So I will be looking to see if you have these numbers in your work when you submit homework and stuff like that. So do we have any numbers that are too low? Are there any numbers that are below 153.5? And the answer is yes. So one outlier is 109, and everything else is above 153. So just that 109 is a problem. And the second question is are there any numbers that are too high? And the answer is no. Our highest number is 214. That's not higher than 225.5, so the only outlier is 109. Next, let's draw the box plot of this data set. So first we have to label our axes, and since our weights range from about 110 to 220, I'm just going to count by tens. So 110, 120, 130, 140, 150, 160, 170, 180, 190, 200, 210, 220. So weight in pounds. All right, so let's first make the box part of the box plot. So with the box part of the box plot, the lower end is at quartile 1, which is 180.5, so, pretty much 180. The upper end is at quartile 3, which is 198.5, so just below 200. So there's your box. Now you draw a line through this box at the median. And the median is 186. So there's your median. Now we have no outliers on the upper end, so the upper end is easy. You just draw a line to the highest value, which is 214. But on the lower end, we have that outlier of 109. So he's a dot. There he is, a little skinny guy. And the bar now extends to the next lowest value, which is just 178. So there's a little bitty bar on that end. And that visual picture just tells you how far away that outlier is from the rest of the data. You can really see it in this picture. Now the next thing, just a little bit of vocabulary that maybe you've seen before, something called a percentile. Now the kth percentile is the number that has k% of the data values at or below that point. So if you're in the first quartile, that's the first 25%, which means you're at the 25th percentile. If you're at the median, half of the values are at or below that point, so that's the 50th percentile. And if you're in the third quartile, that means that, well, that's the first 75% of the data, that's the 75th percentile. And the place you may have seen this is in the context of, say, standardized tests. Suppose you are in the 90th percentile on your ACT math score. What that means is that you scored the same or better than than 90% of your peers on that test. You could also phrase that as only 10% of test takers were better than you. That would be the same thing. Now that we know one criteria to determine if something is an outlier, the question is how do you handle them? Because outliers can have a big influence on conclusions drawn from your data sets. In some instances, they can lead to erroneous conclusions if not treated properly, and they can also mess with certain statistical procedures. But before you throw them out, which you can do if you can justify it, you need to figure out why they exist. So there are 3 cases. First is that the outlier could be a completely legitimate data value and represents natural variability for the group and variables measured. In this case, you can't discard it. You just happen to find somebody who is a little bit different. So unfortunately, to proceed with your outlier. It is possible that you made a mistake in your measurements. So in this case, if you can justify it, you should toss the outlier. And if you're reporting on stuff, you could perhaps report that you did this just to be completely honest about your results. But if it definitely was a mistake in measurement, then it is totally okay to throw it out. And it also could be that the individual belongs to a different group than the bulk of individuals you're measuring. So for example, that guy on the crew team in the previous example, who is 109 pounds. You know, chances are, since he's so much skinnier than the rest of them, he's that collar guy in the boat telling them, row, row, row. So, stuff like that. So, refer back to the rowers from example 4. If you want to describe the weight of all the rowers on the team, would it be reasonable to throw out the outlier of 109? Why or why not? And what function on the team might this rower play? So as we already discussed, yeah, it probably is reasonable to throw this guy out. So I would say yes. He is probably not actually rowing. He's probably that collar guy, keeping all of the rowers in sync. So here's another example of something when you look at the context where somebody is an outlier depending on the context of the situation and sometimes is not. So a male whose height is 78 inches might be considered an outlier among males in a stats class, but not among males who are professional basketball players. So the context of your situation determines when you are or are not an outlier. So give another example in which the same measurement taken on the same individual might be an outlier in one context, but not the other. So here's mine. So for example, at UAF, the median age is 27 of a student, that is. That's because we have lots of non-traditional students who come back to school at later age. The median age is 27, which means being 27 and in school is not unusual at UAF. But where I went to school, or at other schools, so there are other schools that are very much, you go to them straight out of college and you get out in 4 years. So students are between 18 and 22. So one example of such a school would be the school that I went to, a school called Gustavus. And at that school, if you were 27, you would be an outlier. But at UAF, you're not. So the context does affect whether or not you're an outlier. So the next type of continuous variable that we're going to, continuous quantitative variable we're going to look at is something that's bell-shaped. So a bell-shaped curve looks something like this. It's symmetric. The middle value is the mean or the most common value and has the property that most individuals our clump near the center. It's symmetric. And the greater a distance a value is from the center, the more unlikely it is. So the greater distance a value is from the center, the less likely it is. And with bell-shaped data, we use something called the standard deviation to describe the spread. So the standard deviation roughly is the average distance that values fall from the mean. So really roughly, the average distance values fall from the mean. Oh, and that scary sigma symbol came back again. So let's look and see what that is doing. So the x sub i's are all your data values. So you're taking your data values minus your average or your mean, and then you're squaring them, and that's so that negatives don't cancel positives. And then you do that for every single data value. So if you have 5 data values, data value minus mean, whole thing squared 5 times. Then you divide by n minus 1. And the reason it's n minus 1 is kind of complicated. We're not going to go over it in this class. So it is just number of observations minus 1, and the standard deviation is the square root of that. It's very related to a thing called the variance. Notice that the sample variance is just the standard deviation squared, as in we took this expression and squared both sides. That gives us this. So variance is standard deviation squared. Or you could say that standard deviation is the square root of the variance. So that is the relationship. So here are the steps for finding the standard deviation. The first thing you should do is find the mean. Remember, that's x bar. And then for every single observation you have, find the difference between the observation. That's what that formula called the x sub i's. So the little subscript means x sub 1 is first observation, x sub 2 is second observation, etc. And x bar. Then you take these differences that you found and you square them. And then you sum or add them all up. So sum all these square differences found in step 3 and divide by n minus 1. And then lastly, take the square root of this number. At step 4, what you found is the variance. Okay, so let's actually do that for a small set of numbers. So first find the mean. X bar is 22 plus 27 plus 30 plus 21 over 4, and that works out to be 25. And I'm going to combine a lot of those steps into one because I think that it's actually easier. So first the variance, because we find before we square root. That's s squared. And we do data value minus mean squared. So our first data value was 22 minus our mean, which is 25. And we square that. The next data value was 27 minus 25, and we square that. Then we have 30 minus 25, square that. And then 21 minus 25, square that. And we're going to divide that by 4 minus 1. I made a bit of a mistake on purpose here to illustrate something. If you're going to punch this in your calculator in one go, you have to put parentheses in the appropriate place. That numerator has to all be added before you divide. So put parentheses here and here. That tells your calculator to add all that stuff up first. And also you want to do 4 minus 1 before you divide by that number, so put parentheses there. Of course, you could just say that 4 minus 1 is 3, which works just fine as well. So you should try punching this in your calculator to see if you can get it, but you end up with s squared equals 18. So if you need to, pause and punch that in and make sure that you get the same thing. Now that's the variance. So the standard deviation is equal to s, which is the square root of s squared. In this case, it's root of 18, and that's not a whole number, but it's about equal to 4.2. Now, given a bell-shaped curve, you have something called the empirical rule. That doesn't stats, it's a stats class, but it states that for any bell-shaped curve, about 68% of the values fall within one standard deviation of the mean in either direction. 95% of the values fall within 2 standard deviations, and almost all, specifically 99.7%, fall within 3 standard deviations of the mean. So here is that in a picture. Suppose you have your bell-shaped curve. And in this middle is your mean, your x bar. Now 1 standard deviation away, above and below, so over to that end and that end, 68% of people fall within there. The remaining 32%, so there's 32% left, half fall below and half fall above. 1 more standard deviation away, so about there, that's about 2 standard deviations from the mean. There live 95% of everybody, which leaves you just 5% left over, and half of that falls below in that bottom tail and half falls above. And once you go to 3 standard deviations, you've got almost everybody. And that's 99.7%, leaving you just 0.3% left over. And half of that falls below and half of that falls above. That's the picture you should have in your head for this rule. And those numbers come from the fact that the area under this curve is 1, and so the area plus or minus 1 standard deviation is 0.68 or 68%. And proving that these things are true is definitely above and beyond the level of things we're going to do in this course. So let's apply that rule. The typical amount of sleep per night for college students has a bell-shaped distribution with a mean of 7 hours and a standard deviation of 1.7 hours. Use that empirical rule to complete each sentence. So about 68% of college students typically sleep between blank and blank hours per night. Well, that's going to be the mean plus or minus 1 standard deviation, which is 1.7. So on the low end, that's 5.3 hours. On the high end is 8.7. So 68% of students sleep between 5.3 and 8.7 hours. 95% are going to sleep between blank and blank. That will be plus or minus 2 standard deviations. So 2 times 1.7 is 3.4. So 7 minus 3.4 is 3.6. Those poor students sleeping just 3.6 hours, and those lucky people sleeping 10.4 hours. And almost everybody will fall within plus or minus 3 standard deviations. So that's 7 plus or minus 5.1. So on the low end, just 1.9 students will be cramming for a test, and 12.1 hours on the high end. So the verbal SAT scores for students admitted to a university had a bell-shaped distribution with a mean of 540 and a standard deviation of 50. What is the verbal SAT score such that only 16% of admitted students had a higher score? So I think it's helpful to draw a picture here. And the kicker is that 16% times 2 is 32%. Which is related to that 68% in our empirical rule. So we have our bell-shaped curve. The mean is 540. 1 standard deviation away, 590 above. 1 below would be 490. And 68% of people at this university live there in the middle. Notice that that leaves 16% in this upper tail and 16% in that lower tail. So we want the value so that only 16% of students admitted had a higher score than you. So if we're at 490, 68 plus 16, what's that? 78, 84% of people had a higher score than you. If you're at 590, only 16% are above you. So that's the value that we're looking for. So it's going to be the mean plus a single standard deviation, which is 590. If you're at that score, only 16% of the people also admitted have a higher score than you. Now for the next question, what is the verbal SAT score such that only 2.5% of students have a lower score than you? Well, the hint there is that 2.5 times 2 is 5%. So we're probably looking at something that's related to the 95% part of that empirical rule. And so remember that 95% fall within 2 standard deviations. So on the lower end, that's going to be 440. On the upper end, that's going to be 640. And we want the score so that 2.5% of people are below you. Well, that's going to be this 440, or x bar minus 2 standard deviations. Now, in comparing or determining how different a value is from the mean, it might be a different amount in different situations. For example, in example 8, the standard deviation was 50, but in example 7, it was just 1.7. So there's a way of standardizing these z-scores and kind of looking at comparing 2 different things without having to look at different standard deviations. So suppose you know that on an exam, the grade distribution was bell-shaped, and that you were 2 standard deviations above the mean. What percent of students scored higher than you? So bell-shaped curve, you have the mean, 1 standard deviation away, 2 standard deviations away. So if you're 2 standard deviations away, you know that 95% of people fell between the low end and the high end, which means of the remaining 5%, 2.5% fell up there, and 2.5% falls down here. So if you are right here, what percent of students scored higher than you? Only 2.5%. So you can feel yourself pretty proud. And notice that we didn't have to know what the standard deviation was, what the mean was. We just had to know that you were 2 standard deviations above. That's it. And that's what standardized scores are going to do for us. So to standardize a score, you take the observed value minus the mean divided by the standard deviation. and this is called the z-score. And the z-score tells you the distance between the observed value and the mean measured by standard deviations. Data values that are below the mean are going to have negative z-scores, and that's because observed value minus mean will give us a negative number, and data values that are above the mean are going to have positive z-scores. So the question is, how does that empirical rule translate into standardized scores? So 68% of the values fall within one standard deviation. So those z-scores are going to be between -1 and +1. 95% within 2 standard deviations. So they'll have z-scores between -2 and +2. And 99.7% of the values will have z-scores between -3 and +3. So if you get a z-score above 2, you know that you're sort of on the high end. If your z-score is below -2, you know you're kind of on the low end. So suppose the amount spent on textbooks in a semester for college students has a mean of 350 and a standard deviation of 100. Find the standardized z-scores for the given amount spent on textbooks. Are these figures unusually high, low, or about average? Explain. So the z-score is the observed value, which in this case is 100, minus the mean, which is 350, divided by the standard deviation, which is also 100. That comes out to be -2.5. So the negative tells us that this is below the mean, and the fact that it's -2.5, think about that little bell-shaped picture thing. Remember that in this little tail here, there was just 2.5% of people. And -2.5 throws you even further below that cutoff right there. So this means that you're pretty low. Unusually low. And to explain, you could say that you are in the bottom 2.5%. .370 is pretty close to 350, so it seems like that probably is going to be about average, and that's explained by the z-score as well. So z is 370 minus 350 over 100, which works out to be 0.2, which means you're just a little bit above average, so really about average. Note that if you were the average, like if you had spent 350 exactly, your z-score would be 0. That throws you right in the middle. If you spent $500, the z-score is 500 minus 350 over 100, or that is 1.5. So let's think about where that would fall in our picture. So there's your mean, that's 1 standard deviation away. There's 2, puts you right about here. So this is a little high. We'll say in the top, well, at least 16%. But not as obviously, not as unusually low as the first one was. Okay, the final example. So suppose you learn your score on an exam was 80, and the teacher always also tells you that the mean was 70. Are you going to be more satisfied with yourself and think yourself really cool if the standard deviation was 5 or 15? So explain. Okay, so if the standard deviation was 5, then 68% of students have scores between 65 and 75, and 95% of students are between 60 and 80. So if you scored an 80, you are at the top 5%, 2.5%. So only 2.5% of people scored above you. Whereas if the standard deviation was 15, then 68% of students had scores between, so what would that be? 70 minus 15 would be 55. 70 plus 15 is 85. So you are average like. So I think you'd be happier if S was equal to 5. Because in that case, maybe if you end up being pretty high, your teacher might decide to curve that exam. Whereas if it was the second case, there's no reason to curve the exam because there are still people who are 16% are still above the score of 85. So no need to curve then.